Ever wondered why a feather falls slower than a rock, even if you drop them at the same height? Take a moment and ponder on this. It's not just about the weight difference, but there's more to it. Think about how force, mass, and acceleration are intertwined in this scenario. How do they interact with each other to influence the falling speed of these objects? Intriguing, isn't it? Well, don't worry. We're about to unravel this mystery. The answer lies in Newton's second law of motion. Newton's second law of motion states that the force acting on an object is equal to the mass of that object times its acceleration. This law is often expressed using the formula F equals m times a, or F equals sine ma. It's a relatively simple equation on the surface, but each component has a deep and nuanced meaning. Let's start with force, denoted as F. Force is, in essence, a push or pull that can cause an object to change its state of motion. It's this force that sets an object in motion or changes its speed or direction. The unit of force in the International System of Units, SI, is the Newton, named fittingly after Sir Isaac Newton himself. Next, we have m, which stands for mass. Mass is a measure of the amount of matter in an object. It's a fundamental property of an object, an intrinsic characteristic that doesn't change, regardless of where the object is located in the universe. The unit of mass in the SI system is the kilogram. Finally, A stands for acceleration. Acceleration, in its simplest terms, is the rate of change of velocity of an object with respect to time. It's not just about speed, but also the direction in which an object is moving. The unit of acceleration is meters per second squared, or EM(s)². So, when you put it all together, Newton's second law tells us that the force applied to an object is equal to the mass of the object multiplied by its acceleration. This means that if you apply the same force to two objects of different masses, the object with the smaller mass will have a greater acceleration. This law allows us to predict the motion of an object, given its mass and the forces acting upon it. It's a fundamental principle that underpins much of our understanding of the physical world. In other words, the force exerted on an object equals the object's mass times the acceleration it experiences. This simple yet profound equation forms the cornerstone of classical mechanics and has helped us unlock the secrets of the universe. Force, in simple terms, is a push or pull on an object. It's like when you push a door open, pull a drawer out, or when gravity pulls an apple down from a tree. These are all examples of forces at work. But what exactly is force? To put it in a nutshell, force is any interaction that changes the motion of an object. It's the invisible hand that can push, pull, twist, or turn things around us. Now, there are different types of forces that we encounter in our day-to-day lives. Let's start with gravitational force. This is the force that the Earth exerts on everything, pulling them towards its center. It's the reason why we stay grounded and why things fall when we drop them. Next, we have frictional force. This is the force that opposes the motion of an object. Imagine sliding a book across a table. It eventually stops because of the frictional force between the book and the table. Lastly, we have applied forces. These are the forces that we exert on objects. When you push a shopping cart or pull a sled, you are applying a force. Force is not just a simple push or pull. It's a game changer. It can start or stop motion, speed it up or slow it down, or change its direction. For instance, if you kick a stationary ball, it starts to move. That's because your kick, an applied force, has changed the motion of the ball. Similarly, if a moving car suddenly stops, it's because a force, in this case frictional force from the brakes, has acted upon it, and when you throw a ball straight up, it eventually falls down. That's gravity, a force changing the direction of the ball's motion. So, the force on an object can determine how it moves and changes its motion. It's like a puppet master pulling the strings, controlling the dance of everything around us. Understanding forces helps us comprehend why things move the way they do, giving us a better grasp of the world we live in. Mass is the amount of matter in an object, and acceleration is how quickly an object changes its velocity. This is where we delve deeper into the relationship between mass and acceleration. Think of mass as the stuff that makes up an object. It's what gives an object its weight. It's why a feather feels light and a bowling ball feels heavy. The bowling ball has more mass because there's more stuff packed into it. Now let's talk about acceleration. Acceleration is all about change. It's how quickly an object can change its speed or direction. If you're driving a car and you step on the gas, the car accelerates. It changes its speed, getting faster and faster. So how do mass and acceleration relate to each other? Well, they have an inverse relationship. This means when one increases, the other decreases. Picture yourself trying to push a bicycle and then trying to push a car. The bicycle, having less mass, accelerates easily, but the car, with its greater mass, is much harder to accelerate. This is because acceleration depends on the amount of force applied and the mass of the object. The more force you apply, the greater the acceleration. But if the object has a lot of mass, it's going to resist that force. It's going to be harder to accelerate. Let's take a quick detour into space. Imagine an astronaut floating in zero gravity. If they push a small object like a pen, it flies away quickly. But if they push a larger object like another astronaut, it moves away more slowly. Even in the absence of gravity, mass still affects acceleration. So what does this all mean? It means that mass and acceleration are intertwined. They're two key pieces of the puzzle that is Newton's second law of motion. It's a law that governs how we move and interact with the world around us. To sum up, mass is the substance of an object. It's matter, and acceleration is the rate of change in velocity. Together they define how an object moves in response to force. So the more mass an object has, the harder it is to accelerate. Now, how does this law apply to real-life situations, you might wonder? Well, let's dive right into some practical examples of Newton's second law in action. Consider a car accelerating on a road. When you step on the gas pedal, the car's engine generates a force which propels the car forward. Here, the car's mass remains constant, but the force applied causes the car to accelerate. If you were to step harder on the gas pedal, increasing the force, the car would accelerate faster. That's Newton's second law right there in the everyday act of driving. Now, let's think about a person pushing a heavy object, like a furniture. The object doesn't move on its own, right? But when you apply a force, in this case, your muscle power, the object starts to move. The heavier the object, the more force you need to apply to get it moving. That's because the mass of the object is resisting the change in its state of motion, and the force you apply determines the rate at which the object accelerates. Ever played baseball? When the ball is hit with the bat, the force of the bat causes the ball to accelerate rapidly in the direction it was hit. The harder the bat hits the ball, the faster the ball accelerates. And if the ball is heavier or the bat lighter, it will not travel as far. Again, that's Newton's second law at play. Or think about astronauts in space. There's very little gravity there, so the mass of the astronaut and his equipment is virtually unchanged, but the slightest push can send them moving rapidly. That's because the force, however small, applied to a small mass in a low-gravity environment results in a high acceleration. So, Newton's second law isn't just some abstract concept, but a practical principle that governs our everyday life. Whether we're driving a car, moving furniture, playing baseball, or even floating in space, we're constantly experiencing and applying Newton's second law. As you can see, Newton's second law is not just a theory, but a principle that governs our everyday life. In summary, Newton's second law of motion describes the relationship between force, mass, and acceleration. It's a fundamental principle of physics that governs the motion of objects we see around us every day. Let's quickly recap the key points we've discussed. We started by unpacking Newton's second law, which states that the force acting on an object is equal to the mass of that object multiplied by its acceleration. In simpler terms, force equals mass times acceleration, or F equals ma for short. We then explored the concept of force, a push or pull that can change an object's state of motion. Remember, the greater the force applied, the greater the change in motion. We also delved into the concepts of mass and acceleration. Mass is the amount of matter in an object, and it resists changes in motion. Acceleration is the rate of change of velocity of an object. The greater the mass of an object, the more force it takes to accelerate it. We wrapped up by applying Newton's second law in various scenarios, emphasizing its relevance in our daily lives. From understanding why it's harder to push a heavy car than a bicycle, to why a small pebble doesn't hurt as much as a large stone when thrown with the same speed, it's all about Newton's second law. So next time you see something moving, remember, it's all about the force, mass, and acceleration.